Good morning. I welcome you all to this series of lectures on electronic devices and circuits. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering. So today I am going to discuss about the PN junction formation, biasing of PN junction and its characteristics. See, based on the electrical conductivity of materials, the materials are classified as insulators, semiconductors and conductors. So this is based on the electrical conductivity. So if you see, there are two bands, the conduction band and valency band. And the gap between conduction band and valency band is called as the forbidden gap, as shown in this figure. So an insulator, it is a material that offers a very low level of conductivity, or it has high resistance when voltage is applied. That means practically you don't get any current passing through the inductor. For example, paper, mica, wood, glass, quartz and all these things. So the typical resistivity of insulator is of the order of 10 to the power 10 to 10 to the power 12 ohm centimeter. And the energy band structure of insulator is shown in this figure, where the gap between conduction band and energy band, it is approximately 6 electron volts. So for the charge carrier to travel from valency band to the conduction band, it requires an additional energy of 6 electron volts. Coming to the conductors, a conductor is a material which has a very high value of conductivity, and it supports a large flow of charge when voltage is applied across its terminals. For example, copper, aluminum, silver, gold and all these things, these are called the conductors, and the resistivity is of the order of 10 to the power minus 4 to 10 to the power minus 6 ohm centimeter. And in the case of conductor, the valency band and conduction band, they overlap. That means the forbidden energy gap is negative. So practically there is no energy gap. So the electrons can freely move from the valency band to the conduction band. So there are free electrons in conduction band even at 0 degrees temperature. So at room temperature, when the electric field is applied, you get a large amount of current flowing through the conductor. Next, the third category of materials is the semiconductor. So as the name indicates, it is in between the insulator and the conductor. So the conductivity is between the insulator and the conductivity, the metal. So the resistivity is in the order of 10 to the power 4 ohm centimeter. So the two of the most common materials which are used as semiconductors are germanium and silicon. And the silicon has the atomic number 14, the germanium has the atomic number 32. So both have 4 valence electrons. What is valence electron? It is the number of electrons in the outermost orbit. And the forbidden energy gap between the conduction band and valency band, it is approximately of the order of 1 electron volt. See, for the insulator, just now I had told that it is of the order of 6 electron volts, whereas for semiconductor, it is of the order of 1 electron volt. So at room temperature, there are sufficient electrons in the conduction band, and the semiconductor is capable of conducting some current at room temperature. Now, semiconductor types. So the semiconductors are again further subdivided into two categories: intrinsic semiconductor and extrinsic semiconductor. So what is intrinsic semiconductor and what is extrinsic semiconductor? See, the purest form of semiconductor is called as the intrinsic semiconductor. So the conduction in the intrinsic semiconductor, it is either due to thermal excitation or crystal defects. So as we discussed, silicon and germanium are the two most important semiconductors that are being used. And other semiconductor materials are gallium arsenide, and iron display. So these are other semiconductors. In intrinsic semiconductor, the number of electrons is equal to the number of holes. See, there are two types of charge carriers in semiconductors: holes and electrons. Hole is a positive charge carrier and electron is a negative charge carrier, and the number of holes is equal to the number of electrons in intrinsic semiconductor. So what is intrinsic semiconductor? It is a purest form of semiconductor where the number of holes is equal to the number of electrons. So conduction can take place in intrinsic semiconductor either due to thermal excitation or due to the crystal defects. Coming to the second category of semiconductors, that is extrinsic semiconductor. So in extrinsic semiconductor, there is no equality of charge carriers. That means the number of electrons is not equal to the number of holes, depending upon the type of material or depending upon the type of doping. So the current conduction capability of intrinsic semiconductor material can be increased by adding small amounts of impurity to the intrinsic semiconductor. So this adding impurities is called as the doping. So by adding impurities, either the number of electrons will become more or the number of holes will become more. So what is exactly the difference between intrinsic semiconductor and extrinsic semiconductor? Intrinsic semiconductor is the purest form of semiconductor material where the number of electrons is equal to the number of holes. Whereas in extrinsic semiconductor, the number of electrons is not equal to the number of holes, and the conductivity of extrinsic semiconductor is much better compared to the intrinsic semiconductor. So adding impurities, the intrinsic semiconductor material, it becomes extrinsic semiconductor material, and this process of adding impurities is called as the doping. Now let us see the N-type semiconductor. So we have to take the intrinsic semiconductor material. Then if we add a pentavalent atom, then the resultant semiconductor material is called as N-type semiconductor. So if we add small amount of pentavalent atoms, then as you see here, this is a pentavalent atom which has 5 electrons in the outermost orbit. So covalent bonds are formed with the adjacent atoms. So this is silicon, and this is silicon which has 4 valence electrons. And let us say this is arsenic, which is a pentavalent atom which has 5 electrons in the outermost orbit. So these 4 electrons of arsenic, they form covalent bonds with the adjacent electrons of the silicon atoms, and 1 electron is left out here because there are 5 valence electrons in arsenic. So this extra electron, it becomes a charge carrier. So this intrinsic semiconductor, this silicon, which was originally intrinsic semiconductor, now it is having more number of electrons. So that means it is converted to N-type semiconductor. So if the added impurity is a pentavalent atom, then the resultant semiconductor is called as N-type semiconductor. And the examples of pentavalent impurities are phosphorus, arsenic, bismuth, and antimony. So these are the materials which are pentavalent. That means they have 5 electrons in the outermost orbit. So when they are added in small quantities to the intrinsic semiconductor material like silicon or germanium, then that silicon or germanium will become N-type semiconductor material. So the pentavalent impurity, as we discussed, it has 5 valence electrons, and these 5 valence electrons, they form covalent bonds with the adjacent 4 intrinsic semiconductor atoms, and the fifth electron, which is extra or which is loosely bound to the impurity atom, and it gets easily excited from the valence band to the conduction band by the application of electric field or by the application of temperature. So application of temperature is called as thermal excitation. So by application of electric field or by increasing the thermal excitation or the thermal energy, this extra electron will easily pass to the conduction band and it improves the conductivity of the material. Now similarly, for the intrinsic semiconductor material is made to p-type by adding trivalent atoms. So what is trivalent atom? Trivalent atom is an atom which has 3 valence electrons. And what are the examples of trivalent atoms? Boron, gallium and indium. So boron, gallium, indium. So these are the 3 materials which have 3 valence electrons, and by adding these trivalent atoms to the intrinsic semiconductor material, the intrinsic semiconductor material will get converted into p-type semiconductor material. So covalent bonds are formed with the adjacent atoms. So this is silicon. This is also silicon, 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 and this is a gallium, which is trivalent, which has only 3 valence electrons. So you have a vacancy. So the vacancy is called as the hole. So whenever you add trivalent atoms, the 3 valence electrons, they form covalent bonds with the neighboring atoms, and a vacancy exists in the 4th bond. So that produces holes. So the hole is ready to accept electrons from the neighboring atoms. So each trivalent atom contributes to one hole generation, and thus it introduces more number of holes in the valence band. So when the number of electrons are decreased compared to those available in intrinsic semiconductor material because of increased recombination due to the creation of extra holes. So the forbidden energy gap is the energy gap which is between the conduction band and the valence band. So it is approximately 1 electron volt for semiconductor material. And for silicon, and this forbidden energy gap, when you increase the temperature, what happens? The gap reduces, and that is going to improve the conductivity of the semiconductor material. So the forbidden energy gap for silicon is given by this equation. Eg is equal to 1.21 minus 3.6 into 10 to the power minus 4 T electron volts. So this is for silicon. So as you see here, if you increase the temperature, the forbidden energy gap, it reduces. So when the gap reduces, the valence electrons easily rise to the conduction band, thereby the resistance is decreased and the conductivity is improved. So at 0 degrees Kelvin, the forbidden energy gap, it is 1.21 electron volts for silicon. And for germanium, the forbidden energy gap, Eg is equal to 0.785 minus 2.23 into 10 to the power minus 4 T electron volts. This is for germanium. So the forbidden energy gap, it is less for germanium. So both have negative temperature coefficient as far as the forbidden energy gap is concerned. That means if the temperature is increased, the forbidden energy gap reduces, thereby the conductivity is improved for germanium or silicon, or in general for any semiconductor material. the conductivity improves as the temperature is increased. So in a pure semiconductor material, which is intrinsic semiconductor material, the number of holes is equal to the number of electrons. So thermal agitation, it produces new electron hole pairs, and these new electron hole pairs disappear in case when there is a recombination. So the electrons and holes, they move in opposite directions in an electric field because they are of opposite sign, and the current due to each is in the same direction. Hence the total current density in an intrinsic semiconductor is given by this equation: J is equal to Jn plus Jp, and Jn is equal to Q into N mu N E plus Q P mu P E, and N is the charge, N is the number of electrons, and mu N is the mobility of electron, and P is the number of holes, mu P is the mobility of hole, and Q is the charge which is present on the electron or the hole, and E is the electric field intensity. So this we can write it as J is equal to sigma E. E is the electric field. Electric field is voltage by the distance. And what is law of mass action? Law of mass action is like this. For an intrinsic semiconductor material, Np is equal to Ni square. This is called the law of mass action. N is the number of holes, and P is the number of electrons, and Ni is the intrinsic concentration. And suppose if you take a P-type extrinsic semiconductor material where the number of holes is more than the number of electrons, that means the majority charge carriers are holes. So for P-type, the law of mass action, it is written like this: Np Pp is equal to Ni square, where Np is the number of electrons in the P-type material, and Pp is the number of holes in the P-type material, and that is equal to Ni square. So what is Pp? Pp is nothing but the acceptor atoms concentration. So we have added trivalent atoms to convert the intrinsic semiconductor material into the P-type. So Pp is equal to Na. Now from this we can say that Np is equal to Ni square by Na. This is for P-type. Now similarly for N-type, we write like this: Nn Pn is equal to Ni square. So what is Nn? Nn is, we can say Nn is equal to Nd, which is the donor atom's concentration. So Pn is equal to Ni square by Nn, and that is equal to Ni square by Nd, where Nd is equal to the donor atom's concentration, and Na is the acceptor atom's concentration. Now let us see the theory of p-n junction. See, when p-type material and n-type material, when they are brought together, when they are brought close by, then a junction is formed. So if you see the p side, in p side we have the majority charge carriers are holes, and in n-type the majority charge carriers are electrons. So the whole concentration, if you see, it decreases as you go from p side to the n side. In p side it is maximum, and in n side it is minimum. So initially when p and n type materials are brought together, what happens? You are going to have a large flow of current because of non-uniform distribution of charge carriers. So in P side you are having more number of holes, on N side you are having less number of holes. So the hole concentration reduces when you travel from P side to the N side. Similarly, the electron concentration is more in N-type material because the majority charge carriers are electrons. So as you move from N-type to the P side, the electron concentration decreases as you travel from N side to the P side. So whenever there is a variation in concentration, there is going to be a flow of charge carriers from higher density to the lower density. So this causes the diffusion current. So the diffusion current is due to the non-uniform distribution of charge carriers or due to the concentration gradient. So this causes the diffusion current. So as you see here, the holes, there are more number of holes here. As you go from P side to the N side, the number of holes has reduced. Similarly, you are having more number of electrons on N side, and as you travel from N side to the P side, the concentration of electrons is reduced. So slowly what happens, the holes, they move from higher concentration to the lower concentration. So they cross the junction and they move towards the N, they move to the N side. So as the holes, they move to the N side, what happens, they combine with valence electrons which are present on the N side. So what happens when hole combines with electron, both the electron hole pair, it disappears. So some of these, because the holes traveling from P side to the N side, the atoms which are near the N-type atoms which are near the junction, they lose their electrons. So whenever any atom loses its electrons, it becomes positive ion. So when the holes travel from P side to the N side, they meet with the electrons, valence electrons, and the whole electron pair gets recombined and it disappears. So the atoms, the atoms which are there on N side, they become positive ions. So as more and more holes travel towards the N-type region, you get more and more positive charge at the junction. So there is going to be more and more accumulation of positive charge near the junction. So when it becomes sufficiently more, then what happens? It stops further travel of holes from the P side to the N side because the positive ions, they repel the holes. The positive ions at the junction of the positive ions which are present on N side, they repel further travel of holes from the P side. Similarly, in N-type material, we are having majority charge carriers as electrons. So these electrons, they travel towards the P side, and when they travel towards the P side, they meet with holes, and the electron hole pair, it is disappeared, and the atoms which are there on P side, when they lose their holes, actually they become negative charge. So you get formation of negative charge on the P side, or negative ions are produced on the P side. So slowly, when more and more electrons travel from the N side to the P side, we are going to have more and more accumulation of negative charge on the P side. So when it becomes sufficiently large, when the number of negative ions become sufficiently large on P side, they obstruct further flow of charge carriers from N side. They obstruct further flow of electrons from the N side. So at the junction, we are going to have an accumulation of positive and negative charges, positive charge on N side and negative ions on P side. And after some time, when this wall becomes sufficiently strong, the further diffusion current is not going to be there. So this is the accumulation of positive and negative charges at the junction. It develops barrier potential. it develops barrier potential. So this barrier potential is like this. So this is the junction. The barrier potential is like this. So this is, it is positive here because of the presence of the positive ions, and it is negative here because of the presence of negative ions on the P side. So this is the barrier potential. And the barrier potential, it is approximately 0.7 volts per silicon, and it is 0.2 volts per germanium. These are the typical values of barrier potential for semiconductor materials. So a diode, it is a two-layer, two-terminal device, and one terminal is attached to the P side and another terminal is attached to the N side. And the common connecting point where these two materials are joined, it is called as the junction. And the terminal, the ohmic contact which is made on the P side, it is called as the anode terminal, and the ohmic contact which is made on the N side, it is called as the N. It is called as the cathode. That means this is the anode terminal. And this is called as the cathode terminal. So P side, P-type material and N-type material, they are brought together and ohmic contacts are made, and the ohmic contact which is connected to the P side is called as the anode terminal, and the ohmic contact which is made, which is formed at the N-type terminal is called as the cathode terminal. And what is an unbiased diode? See, when the device is formed, if we do not apply any voltage to the diode, it is called as unbiased diode. So that means that this we don't apply any voltage. That means it is connected in zero bias condition with no external potential energy or with no external voltage applied to the junction. But when if the diode terminals are shorted together, few holes from P-type material have energy to overcome the potential barrier and move across the junction, this barrier potential. So this is called as the forward current. Now let us see what happens if you apply some voltage to the diode. So if you apply positive voltage to the P side and negative voltage to the N side, it is called as forward biasing. So what is forward biasing? Applying positive voltage to the, as you see here, applying positive voltage to the P side and applying negative voltage to the N side, it is called as forward biasing. So this figure, it shows the forward biased PN junction diode. So the external voltage which is applied to the PN junction, it is called as the bias. So the positive terminal of the battery or external power supply is connected to the P side or the anode terminal. The negative terminal of the battery is connected to the cathode side or to the N-type material. So this is called the forward biasing of the PN junction diode. So this is the forward biasing of PN junction diode. So here, when the positive voltage when positive terminal is connected to the P side, what happens? The holes which are present on P side, they are pushed and they are made to enter into the N side. Similarly, the negative terminal is connected to the N side, so the electrons which are present on the N side, they are pushed towards the P side. Okay, or you can say one thing. Initially, when the junction is formed, after the junction is formed, the barrier potential develops, and at the junction, On P side we have negative ions, on N side we have positive ions. So the negative ions which are present on P side, they get attracted towards the positive terminal of the battery, and the positive ions which are present on the N side, they get attracted towards the negative terminal of the battery. So these are negative ions, and these are the positive ions. So what happens? The number of charge carriers, the number of charge carriers, or the number of positive ions or the negative ions at the junction, they get decreased because they travel towards the battery. So what happens? The barrier potential width, it reduces the moment you apply forward bias. So when the width reduces at the junction, naturally the barrier potential is reduced. So when the barrier potential is reduced, you are going to have more and more current. So if you increase the forward voltage or the battery voltage more and more, what happens? You are going to have more and more current through the device, through the diode. So as you see here, when the forward voltage is increased, initially when it is less than the barrier potential, you are going to have less current because the barrier acts as a wall and it does not permit the flow of carriers from P side to the N side or from N side to the P side for low applied voltages. But when you apply a sufficient high value of forward bias, the barrier potential width, it gets reduced and the charge carriers easily cross from the P side to the N side or from N side to the P side, and this constitutes forward current. And as we increase the forward bias, the current through the diode, it increases, as you see here. So after the cut-in voltage, it increases. So this is the VI characteristic of the diode. So this is for the silicon diode. Similarly, for germanium diode, if you see the cut-in voltage, because the cut-in voltage is less, even for small applied forward voltages, you get more current. So if you see the germanium diode, what happens for germanium diode? You will get the characteristic something like this. The current starts to flow the moment the forward voltage is more than 0.2 volts. So like this. So this is going for the germanium and this is for the silicon. Of course, germanium, you are going to have more current. So it is going to be like this. So when you apply the forward bias, that means the positive voltage to the P side and negative voltage to the N side, the negative ions which are present on the P side, they move towards the positive terminal of the battery, and the positive ions which are present on the N side, they move towards the negative terminal of the battery. So the barrier potential width, it reduces and the barrier potential is reduced, and the charge carriers, they easily cross the junction, and that constitutes the forward current. So as you increase the forward voltage beyond the barrier potential, there is going to be a steep rise in the forward current. So as we discussed, if the external voltage becomes greater than the value of the potential barrier, that is 0.7 volts per silicon and 0.3 volts per germanium, then the potential barrier's opposition will be overcome and current will start. So the application of forward bias on the junction diode, it results in depletion layer becoming thin and it presents a low impedance path or high conductance path through the junction, so thereby allowing more forward currents to flow. Now let us see what is a reverse bias. Reverse bias is opposite to the forward bias. Applying a negative voltage to the P side or applying a negative voltage to the anode terminal and applying a positive terminal to the N side or the cathode terminal, that is called as reverse bias. So when you apply the reverse bias, what happens? From P side, more holes they travel towards the negative terminal. So you get more and more negative ions on the P side. Similarly, the electrons from the N side, they move towards the positive terminal. So you are going to have more and more number of positive ions. So the number of ions becomes more the moment you apply a reverse bias. So when there is going to be accumulation of more ions at the junction, naturally the barrier width or the junction barrier width is increased, and this increases the barrier potential also. So practically you don't get any current. We do not get any current. So if at all there is going to be any current, the current is going to be due to the minority charge carriers. What are the minority charge carriers? In P side, the majority charge carriers are holes and the minority charge carriers are electrons. Similarly, on N side, the majority charge carriers are electrons and minority charge carriers are holes. So in reverse bias, the current is going to be primarily due to the flow of minority charge carriers, which is going to be very, very less. So when the diode is connected in the reverse bias condition, that means you are applying a positive voltage to the N-type material and negative voltage is applied to the P-type material. So when the positive voltage is applied to the N-type material, it attracts electrons towards the positive electrode and away from the junction. So when the holes on the P side N are also attracted away from the junction towards the negative electrode. So the net result is the depletion layer becomes wider due to the lack of electrons and holes, and it presents a very high impedance path for the charge carriers across the junction. So the result is you get here there is going to be increase in the barrier potential, and it stops the current flowing from it obstructs the current flowing through the junction or through the semiconductor material or through the diode. So these are the VI characteristics of the PN junction diode. In forward direction, after cutting voltage, there is going to be a sharp increase in the forward current. In reverse bias, this is a reverse bias. So here, the up to certain limit, we are going to have very, very small current, and the current is due to only the minority charge carriers. So this current is due to minority charge carriers, and this current is due to this current is due to majority charge carriers. Okay. So this cut-in voltage is 0.3 volts for germanium and 0.7 volts for silicon. And in the reverse bias, where the applied voltage is negative and the current is very small, and this is called as the reverse saturation current. It is almost constant, and this is called as the reverse saturation current, I0. This constant current is called as reverse saturation current. Okay. And in reverse bias, if you increase the voltage beyond certain limit, then a breakdown is going to happen, and the breakdown can be Zener breakdown or avalanche breakdown. So that is because when a large amount of voltage is applied, then the charge carriers they get a lot of momentum, and with high speed they hit the atoms. When they hit the atoms, the valence electrons they are liberated, they are freed from the atoms, and they become, they get multiplied in large numbers, thereby the current is greatly increased. So that a breakdown happens, and this breakdown can cause the damage of the device. This we will discuss in more detail in next lectures. So the VA characteristics of the PN junction diode, I is equal to I naught into e power V by eta Vt minus 1, where I is this is the diode current equation, where I is called the diode current, I naught is called as the diode reverse saturation current at the room temperature, and V is the external voltage applied to the diode. It can be a forward voltage or reverse voltage. In forward bias, V is positive. In reverse bias, V is negative. And eta, it is constant. And it is 1 for germanium and it is 2 for silicon. Eta is equal to 1 for germanium and it is 2 for silicon. And Vt is equal to Kt by Q. And that you can also compute it as T by 11,600. T by 11,600. So that is a volt equivalent of temperature. So that is a thermal voltage where K is the Boltzmann's constant, which is 1.38 into 10 to the power minus 23 joules per Kelvin, and Q is equal to the charge of electron, which is 1.602 into 10 to the power minus 19, and T is the temperature of the diode junction, which is degree centigrade you have to take, and you have to add 273, and at room temperature T is equal to 300 degrees Kelvin, because at room temperature we take room temperature it is T is equal to 300, because the room temperature, if you take 27, then 27 plus 273 we get 300. So 300 degrees Kelvin. So Vt is going to become 26 millivolts. So as you see from this equation, I is equal to I naught into e power V by eta Vt minus 1, and eta is equal to 1 for germanium and 2 for silicon. And because it is coming on the denominator side, we get large magnitudes of current for germanium diode, because eta is equal to 1, and for silicon we get relatively less current because eta is equal to 2, and that is coming in the denominator side. So this is called the diode equation, and I naught is the reverse saturation current. So with this I conclude today's lecture on the theory of PN junction and the diode current equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.